All right, part two, habitable zones. So the habitable zone is going to depend upon the type of star that you have. So you can have a small red star is habitable zone. It's going to be closer to the star because it's just not giving off as much energy, as much light. And then you have a star like the sun, where the habitable zone is a little bit further away. And there it's going to still be in a range because if you're too close, you're going to be too hot. If you're too far away, you're going to be too cold. The other thing you're also looking for is the evidence of heavy elements like carbon, nitrogen, oxygen, because you need those to sustain life forms, particularly carbon-based life forms. And you also need to be far enough away such that you're not getting UV radiation or also have some kind of protection in your atmosphere. Like here on Earth, we have the ozone layer, which blocks a lot of the UV radiation from striking the Earth. That's why the ozone hole was such a big issue about 20, 25 years ago, because as it was eroding, more and more UV light was being let into um, the atmosphere. And the habitable zone is going to be all over the place. Again, if you have a really big blue bright star, much like Betelgeuse or Orion in Orion's nebula, which we will see here shortly, is that its habitable zone is going to be very far away. It also gives off a lot of radiation. So you need to be really far away from the star so that you don't get cooked. And then you have the zone shrinks as you move to cooler stars. There's also special spots in galaxies too, because we suspect that at the center of every galaxy is probably a black hole. That's what's causing this rapid rotation of galaxies. That's one of the explanations for all the missing mass that we see out in the universe as well. Because galaxies tend to spin faster than we think they should, given the mass that we can see. And of course, the mass that we can see are the things that give off light. So generally, if we're going to be looking for um, life in a galaxy, particularly in these spiral galaxies, is where we expect to find it. We'll talk about the slight difference. Spiral galaxies are younger galaxies, which means that they've had the benefit of supernovas throughout the lifetime of the universe. And generally, if you're in close in a spiral galaxy, that's also experienced a lot of supernovas. And so if life existed there, it probably doesn't anymore because it was blown up via a supernova. And those supernovas then fed the outer rings that have all the carbon, nitrogen, oxygen, and they also have a lot of gas particles and dust particles still remaining. And that's likely where we would find life, somewhere out in one of the rings. And we exist in one of the Milky Way's rings. And then if you want to see a animation of what a habitable zone looks like and how it might change over time, this is a pretty good animation from Australia. Now, we've seen in our DAISY lab, the NetLogo lab where you have to keep the flowers alive, that over time the sun does get bigger. Okay? And that means that its luminosity goes up, right? Which means that over time our Earth is going to get warmer, period. And we're talking about over a course of billions of years. So it's a slow, slow process. Right? Now, um, earlier in the Earth's lifetime, right, the sun actually wasn't as bright as it is now because it was still getting underway, it was still forming, it was still undergoing fusion in its core to reach where it is now. Um, but even a slight 1% difference in temperature can lead to significant changes on the planet, as we're now seeing with climate change, and then as we saw with the ice ages, because the planet cooled, and it was probably due to a lack of activity around the sun's surface, which is an indicator of how much energy is being given off by the sun. So, what's going to happen to our sun? So, our sun is somewhat of a reasonably boring star. It started off as a big ball of gas. It collapsed, and now it's been pretty stable. We're here. We're 4.5, 5 billion years old. We're going to keep going. We're slowly going to get bigger, And then we're going to start to shed our outer layers because the sun's just going to get so big that the gravitational force that retains those layers around the sun just will not be enough to counteract the external pressure of all the fusion happening inside of the sun. And it's slowly going to turn into a red giant. Right? Going to get big, and then eventually all of these outer layers will just kind of be shed, and then what will happen is the remaining part of the star will collapse in on itself, and you'll get a little tiny bit of a pushback, and you're going to create a planetary nebula, and our sun's going to slowly just turn into a little white dwarf, and that's where we're going to be. Now, to give you a sense of scale on where the sun is going to get in terms of the size, is that it's going to get quite a bit bigger. Right? So you can see a little dot where right now that's our sun. This is how much bigger our sun is going to get. Because as the sun goes through its fusion life cycle, it's going to take more and more energy for it to fuse, and that's going to cause more and more of an explosion to push the outer layers away. You can see it completely encompasses Venus. Okay, and so now Venus kind of becomes a new Mercury. So Venus gets very, very, very hot, and we also become a pretty hot um, in Earth because look how the surface of the sun is quite a bit closer to us. Now this isn't new, right? As we've seen, is that the sun has changed over the course of its lifetime, and it will continue, but particularly in the warmer periods. Now, if we begin to look at the Earth's temperature, we've seen that it has also stayed the same, but it's been reasonably stable, right, for basically the life of the Earth. So it was warmer way back, hundreds of millions of years ago, as we've seen, in dinosaur movies and so forth like that in the fossil records. Then it went slowly through a decay. It slowly cooled off, right? And then it's kind of fluctuated up and down a bit. Right? Then we hit a couple of major ice ages, right? And then we went back up, and now look at us. We've been really stable here, okay, for the last 10,000 years. I mean, remarkably stable, okay? And this is where we evolved, right? So we needed all of this to eventually get to here in order to allow humans to evolve. So what we're beginning to suspect is that the habitable zone is actually fairly small given these variations, because if this cooling and then leveling off hadn't happened, it would have probably been too hot for us to evolve as a species, because then why else would the dinosaurs have gone away? The meteor wasn't the real reason why they ended up getting killed. Part of it was this cooling off of the atmosphere, and um, various other issues that began to emerge because of that. And then the meteor finished them off. So, life elsewhere. So, where would we look? Well, SETI is looking to search for extraterrestrial intelligence. You can download their app into your computer and you can have it analyze SETI data. There's so much data that it just can constantly be analyzed. So they have the algorithms written where it'll just sit and analyze data while you're not using your computer, because there's a lot of computational power that tends to just sit idle. So as we have seen, what do we look for? Well, we're going to look for distance. We're going to see if we see seasonal changes on the planet in some way, and this will mostly be detected through UV type of radiation changes, infrared types of changes, things like that. We're going to look at spectroscopy. What do we see in the sun's atmosphere in particular? What elements are we seeing? Are we seeing oxygens? Are we seeing nitrogens? Are we seeing irons? Because that will also tell us what might make up the composition of the planet. Because if we don't see any irons or oxygens in the star, that is highly unlikely that we will find a habitable planet, because it's just too young. And you probably don't have enough carbon and oxygen, enough of those heavier elements in order to sustain life and form life. So how we're doing this with the Kepler satellites. And this is the same model as the other planet hunting satellites that are out there. And basically what it does is it gets pointed to a certain part of the sky, and it's actually a very tiny area of the sky. Okay. Um, and so we're only looking at about a 0.5% of the entire night sky with one of these telescopes, which means a lot because we found a lot of planets by just looking at this very narrow scope, right? If we begin to look at the whole sky, we're likely to find a lot more planets. And how we do this is we can point the telescope at a star and we know what its luminosity values are. And so what we're looking for is basically an eclipse of that star by another planet. And so when the planet goes in front of that star, right, its luminosity value should dip some because some of the light is being blocked by that planet. So knowing that, we can calculate out the size of the planet and how far away from the planet the star is, because we would also be able to track how long does it take for the planet to transit or go across the sun, because that's going to tell us the time, and that time is directly related to its orbital speed around the sun. And so then if we know the mass of the sun, right, and then we roughly know probably the mass of the planet because we know its size, is that then we can figure out how far away from the star it is based upon this luminosity drop. Right? So we're basically looking for transits. And these are all the planets that we have found by our one Kepler telescope. We have a couple more out there now. We'll look at those here in a second. All right, a lot over a course of basically 4 years. Okay, now why I have this graph up is, well, look at the size over here, size of the planets. Right, we found a lot of big ones, which isn't surprising because those are easier to detect because it's easier to measure when you're having a lot of light blocked from the sun. So it's a data effect of being able to see an effect happen. Whereas down here, right, we don't see as many small ones, which is that they're harder to see, right, because you're not getting as much light being blocked. So it might overwhelm the satellite in terms of too much light, and you might just miss the transit. But notice there's a lot of them that are roughly the size of the Earth, even given those limitations. So here are some of them. All right, so this is updated as of 2015. Kepler's gone offline and we're bringing on a couple of new satellites now, so we'll be looking at those shortly. So we found a number of them, and when you look at these pictures where they got the little drawings that look like Earth, we don't know that they look like that. Is that it's an artist rendition of what they might look like, because otherwise they're just kind of blobs, and so it's an artist trying to visualize what the planet might look like, and it gives you a way of looking at it. So when you look at Tau Ceti, which is one of our closest Earth-like planets, we believe, it doesn't really look like Earth, right? The only reason why it looks like Earth is because, well, Earth looks like Earth and it's close enough, right? And you can begin to get a sense of scale. So here's the Earth. Notice most of them are relatively small, right? In terms of Jupiter, but large relative to the size of the Earth. Again, it's easier to see planets that are bigger. Right? There's a few. Right? So now, given that we can find planets, what's the likelihood that one of them has life on it? So what we're going to do in the next section is we're going to explore the most unscientific science equation that exists, known as the Drake equation.